Hi guys, this is Dr. Ricardo. We are going to do chapter 17 now. The video notes will probably be in 3 or 4 sections, and the first section that we're going to talk about is solutions that are buffered. So here we go. So the idea of having both the acid and its conjugate base in the same solution is called the common ion effect. So if we read this note here, it says a shift in the ionic equilibrium caused by the addition of a solute that provides an ion that takes part in the equilibrium. So a classic example is the system of acetic acid and sodium acetate. Okay, so we've been working with acetic acid. We know it's Ka. It's 1.8 times 10 to the minus 5, so that's the Ka. And we can abbreviate acetic acid as HA or HAC is what most people usually do. So you don't have to write out the whole molecular formula every time. If you approach it from the acetic acid side and you look at the hydrolysis of acetic acid, you add the acetic acid to water. The acetic acid donates a proton to cause acetate, right, to make acetate, and the hydronium ion. So that's the equilibrium. So if we just had acetic acid originally and we added it to the solution, the equilibrium would be approached from the left-hand side. Like we'd start out with this and we'd end up with an equilibrium that originated from only acetic acid. Okay? Another way to reach equilibrium is to start with a solution of sodium acetate. That's the conjugate base of acetic acid. So instead of HAC, it's AC minus. Okay? So this is the Ka for this guy. If we need the Ka for acetate, the Kb for acetate, we just need to take Kw, which is 10 to the minus 14th, and divide it by Ka. So this guy's going to be a smaller number, and we'll calculate that in a bit. Okay, well, if we just took sodium acetate, put it into solution, then what would it do? Well, it would react with water, remove a proton from water, make acetic acid, and make hydronium. So you can approach the equilibrium from this side by putting acetic acid in, or you can approach the equilibrium from the other side by putting sodium acetate in. What would happen if we put both of them in? Okay, so we take a solution, take some water, add acetic acid to it, stir that in, then take acetate, sodium acetate, which is a salt. Okay, so take crystals of it, weigh them out, stir that into the solution. You would wind up, before you approached equilibrium, you'd wind up with both of these ions in large quantities, quantities that you couldn't neglect, okay, because we added them from the outside. So that's a buffered solution. When you have like 0.1 molar of this and 0.2 molar of this, you have big numbers of these two species, okay? All right, so in terms of the common ion effect, taking our original sodium acetate solution, if we look at it from Le Chatelier's principle, and all of a sudden I add external sodium acetate to my acetic acid, well, all of a sudden it's going to say, hey, there's too much acetate in the solution, there's too much acetate in the solution, so the equilibrium would shift back to the left. So that's what this arrow is showing, is what would happen by Le Chatelier's principle if we added external sodium acetate. So here's our first example. We have a solution that's prepared to be 0.1 molar in acetic acid and 0.2 molar in sodium acetate. So if we think about the scientist who's making up the beaker, right? Let's say you were going to make a 1 liter solution at the end. You take 0.1 moles of HAC and 0.2 moles of NaAC, sodium acetate. Then put a little bit of water in, get that all to dissolve so it's nice and homogeneous, then fill it up to the line so that you have a total solution of 1 liter. If you do that, and this is all homogeneous and those ions are in the beaker, sorry, my wall of this side is a little too low, okay, then what would it be? It would be 0.10 molar HAC and 0.20 molar AC minus. So they're both in there. Okay, so how does a solution like that, a buffered solution that has both the acid and its conjugate base, how does it come to equilibrium? Okay, all right, so you can start out with either the reaction for the acid hydrolyzing or the base hydrolyzing, and either way, you'll get the same answer. So it doesn't matter which of these two you start out with. You don't have any excess hydroxide or hydronium left, right? These are both 10 to the minus 7 because you started with water. You don't have any of this. So you're going to approach equilibrium either from this side or this side, but you got to pick one. So the one that people ordinarily picked is they pick the acetic acid one because we already have the Ka. We don't have to do this calculation. Okay? So we're going to say if I approach the equilibrium by the sodium acetate reacting with water, again, this is the hydrolysis reaction, to make acetate and hydronium, I can make an ice table and use the concentrations that I have from up here. So my original concentration of acetic acid was 0.1. My original concentration of acetate was 0.2. We don't have any hydronium, right, which I wrote over here in parentheses 10 to the minus 7 because that's pH equal to 7. So that's basically nothing. And then water we don't care about because it's a huge excess and it's not going to be in the equilibrium expression anyway. Okay, why do we start out by going to the right? Because we got to fill in this 0. Even though I have a number here and a number here, you say, well, why can't it go this way first? It can't because there's no 0 on this side, right? This guy is 55 moles per liter. There's plenty of water. Okay, so you got to go to the right initially. That's why we're subtracting x. The way I'm going to approach equilibrium is this guy's going to go down a little bit, this guy's going to go up a little bit, this guy's going to go up from 0. At equilibrium, I got 0.1 minus x, 0.2 plus x, that's just summing these up. 0 plus x is equal to x. I can definitely drop the x here and drop the x here. Boy, if I could drop it before when I just had regular acetic acid, I can really drop it now because adding the excess sodium acetate is going to retard this reaction from going too far to the right. So it's going to go less to the right than it would have if this was a 0 here by Le Chatelier's principle because you've got a number here. So this number is going to be a lot less, a lot smaller. So x is going to be tiny. Okay, so 0.2 plus x is basically 0.2. 0.1 plus x is basically 0.1. Plug them into the Ka expression, this times this divided by this. And you'll see, just rearranging, I don't have any, take a square root in this case, right? I've got all numbers here, right? I can take my Ka, which I know the value is 1.7 times 10 to the minus 5. I use 1.7 in this case, right? Let me see if that's right. Yeah, 1.7 times 10 to the minus 5. So I take that number and multiply it by 0.1, right? If I cross multiply, that comes up here, divide it by 0.2. So x is hydronium, so that's the way I'm going to get the pH. If I have the hydronium ion concentration, how do I get the pH? I take the negative log of this number. So put this number in your calculator, take the log of it, right? The log base 10 of it. If this is 10 to the minus 6, then guess what? This is going to be around a -5 or -6, right? And then it's going to come out to -5.07. You're going to drop the negative sign because the definition of pH is minus the log of hydronium. Okay? So practice that yourself, putting this number into your calculator and making sure that you can calculate the pH. Okay? So here's some more examples of buffers. This really was a buffer. We called it the common ion, but anytime you got the acid and the conjugate base in large quantities in the same solution, the solution is buffered. Definition of a buffer. A buffer is a solution characterized by the ability to resist changes in pH when limited amounts of acid or base are added to it. It's prepared by placing equal molar amounts of an acid and its conjugate base in solution, or a base and its conjugate acid. So you can also make a pretty good buffer with ammonia and ammonium. Okay, here's two examples of same buffer, Okay, well, actually, I have two different buffers, but example A, I have the weak acid ammonia and its conjugate base ammonium. So how did I get this? I added some ammonia, which is a liquid, to the solution. Then I added some ammonium chloride, which is a solid, to the solution. I mixed them up. Turns out I have a very high concentration, right? In 1 liter, I have, for each liter, I have 1 mole per liter of ammonia, and I independently put 1 mole per liter of ammonium chloride. So they're both in the water. Okay? I could take a smaller quantity of this and it would work exactly the same way. But if you want to, you can think about it as a whole liter. Okay? Any amount doesn't matter because we're dealing with concentration, right? Concentration is the amount of moles per unit volume. Okay? So if I have half of this amount, I'm still going to have the same concentration. Right? What would happen to that solution if I arbitrarily got another a beaker filled with concentrated HCl, right? Concentrated HCl. Hydrochloric acid is a strong acid. This thing completely dissociates to give you hydrogen ions and chloride ions. Those chloride ions, as soon as they hit the water, hook up with the water to make hydronium ions. So you can think of this or this, right? Another way to look at it, all the way to the right, donates to ammonia, to water. So either way, same reaction. So adding H plus is like adding hydronium, right? We know those two things are equivalent. So guess what? If I add H plus to this, I have my 2 superheroes in here. I have Batman and Robin, right? So I don't know, Batman and Robin aren't usually considered superheroes, but I'm going to use them as a case. So I've got Batman and Robin. So the ammonia is Batman. So Batman says to Robin, "Oh, they're adding external acid. I'm going to handle it." So ammonia reacts with this very dangerous hydrogen ion to neutralize it, to take the strong acid H plus and make the weak acid ammonium. So Batman does the job whenever you add excess acid. Okay? So now, if this was your stomach and you drank HCl and you had this buffer in your stomach, you would neutralize it and you'd go from having something that's very dangerous in your stomach, strong HCl, which actually you do have in your stomach, to something that's much weaker, ammonium. So you're converting the strong acid to a weak acid. So that's very effective. Okay, what happens? Different situation. I have my buffer set up, I get another sample of it, and all of a sudden, I'm going to bring a different bad guy in. I'm going to bring the hydroxide ion in the form of sodium hydroxide, the strong base sodium hydroxide. Soon as sodium hydroxide dissolves, it makes sodium ions and hydroxide ions. Who cares about the sodium ions? They don't do anything. It's these guys that are very dangerous. Well, in that situation, Batman and Robin are hanging out. Robin says to Batman, "Batman, don't worry. It's a base. I'll take care of it." So ammonium is perfectly suited to react with hydroxide. Look at that. Ammonium has an extra proton ready to be delivered to hydroxide to make ammonia and water. Okay? So this top one here, if you wanted to view it in a fancier way, it's still going to be a neutralization reaction, right? These reactions here, these two reactions here are not hydrolysis reactions, they're neutralizations. Why would the H plus react with water in a hydrolysis reaction when it has a much stronger base to react with? Why would hydroxide react with water when it has a much stronger acid to react with? Okay, so another way to look at the top one is hydronium plus ammonia. The hydronium donates to the ammonia to make the ammonium and water. In hydrolysis reactions, you react with water. In neutralization reactions, an acid reacts with a base to create a salt and water. You make water, so that's why it's neutralizing it. Okay, so those are the neutralization reactions for the ammonia-ammonium buffer. Okay, here's a different buffer. This is 1 molar solution in acetic acid and 1 molar in sodium acetate. So they're both sitting there. So I've got my Batman and Robin again. Okay, so here comes acetate. Here comes the dangerous strong acid, hydrochloric acid. Just like before. Let me find that one. All right. Here comes hydrochloric acid. Hydrochloric acid, as soon as it hits solution, makes hydronium and water. We need to get rid of that hydronium or that H+, whichever way you want to look at it. Here I wrote it down as H+. So Batman and Robin are hanging out. This time, Robin says, Batman, they've added strong acid. I'll take care of it. So the sodium acetate that were originally added, that made acetate, reacts with the hydrogen immediately to make to make acetic acid. So I take the weak base and the strong acid to make the weak acid. So I get rid of a strong acid and replace it with a weak acid. So you're not going to get an ulcer, okay? It's going to buffer the system. It's going to make it change much slower. We want to have buffered systems in our bodies, okay? In our blood, we have a carbonate buffered system. A lot of places in our body, everything is buffered. Okay, so how about if I was going to add the strong base hydroxide in the form of sodium hydroxide? Well, in that case, Batman and Robin are hanging out, waiting for bad guys to come. Here comes the bad guy. The bad guy is the strong base hydroxide. They're adding hydroxide. They're adding hydroxide. Batman says to Robin, Robin, don't worry, I've got this. So now this guy's just hanging out, minding his own business. And what does this Batman do? The acetic acid reacts with hydroxide by donating a proton to it to make water and acetate. So I replace the very dangerous strong base hydroxide with the weak base acetate. These guys, both of these reactions, all four of these, 1, 2, 3, 4, are called neutralization reactions. They go all the way to the right, and they are defined. They are defined as acid plus base makes water and a salt. What's the salt? The salt is the conjugate base of this weak acid. Good. Okay, how do you measure the pH in buffers? It's actually very simple, right? We kind of did one in the example before. So let's take a look at this example. In this example, instructions for making up a buffer say to mix 60 milliliters of 0.1 molar ammonia with 40 milliliters of 0.1 molar ammonium chloride. Question is, what's the pH of this solution? So first thing you have to realize is that since you're mixing two things, you've got to take into account that both of them are going to be diluted, right? So let's take a solution of one of them, right? We don't need 3 beakers. We can just add one to the other. So I'll make a bigger beaker with a lot of space here, and I'm going to put my 60 milliliters of ammonia, right? The buffer, 60 milliliters of ammonia, and what's its concentration? 0.1. Okay, and I'm going to take another smaller beaker that has 40 milliliters. Okay, I put one more significant digit here in here so that everybody has 3. So in the end, our pH, we can measure it to 3 significant digits. I'll show you how to do that. Okay. All right, so this guy is 40 milliliters of, this one is also 0.1. And it's ammonium chloride. Pretty good with that? Now, listen, who cares about chloride? I can already get rid of that, right? When this dissolves, it just breaks apart and the chloride is hanging out in solution. Chloride does not contribute to the pH because it's the conjugate base of hydrochloric acid, which is a strong acid. So it's that counts. So my buffer is between these two things. Okay, when I add this to this, folks, very important, don't leave this step out. What's the total new volume of the solution? 100 milliliters. So you have to account for the fact that these two numbers are not going to be 0.1. You're going to dilute them. So here's one way of viewing the dilution. A lot of you guys do the molarity initially times the volume initially is equal to the molarity at the end. These should be capital M's, okay? Times the volume at the end, okay? But basically, I'm going to do that in a different form called a dilution factor. So this dilution factor here is a ratio of the old, I want you to look at it in a different way, okay? It's a ratio. Basically, I'm going to be solving for M2. So let me do that. M2 here, right, is going to be M1 times V1. I'm going to just write it over here, over, and then where does this guy, if I'm solving for V2, this guy's going to come over here, V2. Okay? So I just take a break, do the algebra yourself, and realize that the new molarity anytime is the old molarity multiplied by this thing over here, this ratio. Okay? This ratio here, the old volume over the new volume, is called the dilution factor. Okay? And why is the dilution factor important? It's a faster way so that you don't have to go do all this algebra every time. So you say, if I want to know the original concentration of the ammonia in the big beaker after they mix, after they're mixed together but before they start to react, I take the 60 milliliters that I started with divided by the new volume, 100 milliliters. See, the old volume over the new volume times the old molarity. Kind of makes sense. The new stuff is going to be 60% as strong as the old stuff. 60 out of 100. So what's it going to do to the 0.1? Going to make it 0.06. Okay. What about the ammonium? Well, we took 40 milliliters and mixed it with 60 to get 100. So don't put 60 in the denominator. You put the new volume in the denominator. So 40 out of 100 times 0.1. You guys can't see the decimals so well. Okay. A little bit hard to see. Okay. Equals 0.04. All right. Now we have the concentrations of the two materials in the beaker that we're interested in this bigger beaker, the beaker with 100 milliliters in it. Okay, so what are we going to do? We're going to do the hydrolysis reaction. We can't do neutralization because we don't have any excess hydronium or hydroxide. So the ammonia or the ammonium, you could have started with either one, but we're going to start with ammonia because it's the base that we can look up on the table. So ammonia reacts with water to make ammonium and hydroxide, right? Conjugate acid, conjugate, this is the base, here's his conjugate acid, this is the acid, it's donating a proton to ammonia, here's his conjugate base, okay? What's the initial concentration of this? 0.6, right from here. Who cares about water? It's in huge excess. This guy's 0.4. This guy's 0, right? Basically 0. Why did I put a little approximate sign? Because we know in water it's 10 to the minus 7th, but that's basically 0. Okay, why does this guy go down by x? Because I got to fill in that 0. The equilibrium initially is going to start out by going to the right. Down by x, up by x, up by x. 0.6 minus x, 0.4 plus x, x. Okay, I can definitely drop the x in a buffer solution because this is going to go even less to the right than it would have if the ammonia wasn't here, and we would have dropped the x even if this 0.4 wasn't here. So I can drop it from here, and I can also drop it from here. So you're not going to get a classic x squared question. What you're going to get is this stacked up ratio here, which is the concentration of the base, of the ammonium divided by the concentration of the ammonia, right? Because it's this times this divided by that. We look up Kb in the table, okay? Kb is 1.8 times 10 to the minus 5. It's interesting that ammonia has a Kb of 1.8 times 10 to the minus 5, and acetic acid has a Ka of 1.7 times 10 to the minus 5. So they just happen to have similar numbers. So it's less numbers for us to memorize. Okay? That's why we use them as examples so much. All right. If I have all this, now remember, this is given to you, right? Kb was given to you, should have been given to you in the question. I would write it up here in a test. So you have this, so you're going to solve for x. So this guy's coming up, this guy's going down. X is 2.7 times 10 to the minus 5, among other things, right? X is a lot of things, but the most important thing it is hydroxide. Listen, guys, if it's hydroxide, you're not done when you solve for x. You got 2 more steps. One, you better identify for me what is x. So tell me x is hydroxide. Next step, how do you get from hydroxide, which is now we've discovered is 2.7 times 10 to the minus 5, all the way to pH? Well, there's two ways of doing it. I'm going to do it the pOH way. So the first way I'm going to do it is take the log of the hydroxide ion concentration and throw away the negative sign. That'll give me pOH. Okay, so if I take the log of this number, it's going to give me a negative 4.57. Okay, I promise you. Take the log and put parentheses 2.7 times 10 to the minus 5. Take the log of that number, you'll get negative 4.57. Then negative will cancel out. So the pOH values will be positive. If the pOH is 4.57 times 10, 4.57, what's the pH? Well, we know this very important equation. pH plus pOH is always equal to 14. This is going to be the case, folks. This is going to be the case whenever the temperature is 25 degrees. Okay, any aqueous solution. Remember, even the water in the Passaic, the water in the Gowanus, pick the most polluted river in the world, this still holds. Okay, the pH in the Passaic might be pH 5. That makes the pOH 9. 5 and 9 equals 14. Okay. Good? All right, last step. 14 minus 4.57 gives me 9.43. So this buffer is basic, okay? Well, why is it basic? It's basic because ammonia is a stronger a stronger base than ammonium is an acid. So even though I have I have a higher concentration of this one too. So two reasons. One, this guy's a higher concentration, but also this guy's a better base than this is an acid. Right? How do I know that? Because it's kind of cool. Right? We know Kb for ammonia. We said it was 1.8 times 10 to the minus 5. So the Ka, how strong of an acid, how good is ammonium at dropping off one proton? Well, that's Kw over Kb. All right, so this is going to be around 10 to the minus 9, so much weaker. All right, so let me do that for you. I have my calculator someplace. Okay. All right, so parentheses. Oops, sorry. 1e minus 14 divided by, open the parentheses, 1.8 e minus 1.8 e minus 5. Boom. 5.55, so I'm going to make that 5.6 times 10 to the minus 10. So this is a much better base than this is an acid. So if they're battling it out, who's going to win? Even if these were equal molar concentrations, let's say these were both, instead of 0.06 and 0.04, if they were both 0.05, they're both the same, this solution would still be basic because this is a better base than this is an acid by a lot, right? 5 orders of magnitude. 5 orders of magnitude is 100,000. There's 100,000 times better acid than this is a base. Oh, excuse me, base than this is an acid. Okay, so what's going to happen is that in all of our acid-base systems, right, we're going to drop the X. So very quickly, you can assume that if you're going to drop the X, the concentration at equilibrium of the acid part of the buffer is equal to the initial concentration, right? That little 0 means initial concentration. And the concentration of the conjugate base is going to be equal to the initial concentration. So Ka is always going to be equal to hydronium times the conjugate base over the original concentration of the acid. Okay, so that's going to happen every time. Look, it happened here, right? Ka was the concentration of the conjugate acid over the base. The 0.04 went in the 0.04 went in the numerator, the 0.06 went in the denominator. Well, if that's always going to happen, you can make a cool little equation, right? Rearrange this, just do algebra to go from here to here, solve it for hydronium. Why are we solving it for hydronium? Because we want pH, right? pH is really important to us. So if I solve this for hydronium, this guy's coming up here, and this guy is going down here. Good? So hydronium is equal to Ka times the initial concentration of the acid divided by the initial concentration of the base. This is after you do all the mixing. Now, a lot of times, I'm just going to give you the solution already, make it easier for you so you don't have to mix it. But if you do have to mix two things, after you take care of the dilution, you can use this equation. So this is pretty powerful. Well, people have these two dudes, right? let's assume they're dudes, okay? They might not be. Maybe these two people, okay? Henderson and Hasselbalch put together a little equation, right? And they get their name on it for the simplest thing in the world. Basically, what they did was take the log of everything, right? So if you take the log of everything, I'm not going to derive it for you, but you could kind of see how this would happen. You can say that the pH is equal to the pKa plus the log of whatever the initial concentration of the conjugate base is divided by the concentration of the acid. So go back up to here, right? It's probably a little more appropriate to go back up to here and you see everything in the right place, okay? So that's the case. All the minus signs are going to cancel out, and I have the derivation on the next page. You can go through it yourself. So this is kind of powerful. If you want to know the pH of a buffered solution, you take the pKa of whatever the acid is that's involved, right? So how do you get the pKa? You take minus the log of the Ka, right? So the P of anything is minus the log of that thing. So pKa, maybe this is a new one, is equal to minus the log of Ka. Okay. So we can do our acetic acid one if we want in a second. Okay. All right. So the pH is equal to the pKa plus the log of whatever the conjugate base is divided by the acid. Okay, these are the initial amounts. They come right out of the question. You don't have to make an ice table. You don't have to do anything. It's right there for you. So some people like this better. Some people like to go back to this. Okay. You can do the same thing for the system that we just did, was one that's naturally a base. Because how does a base react? A base reacts with water to make the conjugate acid. This would be the ammonium, this would be the ammonia, and hydroxide. Okay? So since we're going to be able to drop the X's, the concentration of the base at equilibrium is going to be equal to the concentration of the base that you initially started with. Because at equilibrium, it's just the initial minus X. Well, X is very small. Same thing here. This would ordinarily be the equilibrium concentration would be the initial amount of HB that you put in plus X. Well, if X is very small, these two things are going to be the same. The amount that I give you in the solution is going to be the equilibrium amount. Okay, well, Kb always is this times this divided by this. So we can replace these with the initial concentrations because X is small. So what do I get? Hydroxide is equal to Kb. Right, all from here to here is just algebra times the concentration of the base divided by the concentration of the conjugate acid, that's this guy. Right, so from here to here, all I did was algebra. And then I took the logs of everything. And I took the log of everything, and actually the negative log of everything, I get this equation. The pOH of a solution is equal to the Kb plus the log of the conjugate acid divided by the base. So it's still going to be products over reactants in here. Look at this one. And look at this one. This one too. This is products over reactants just like you'd expect. Okay? So you would use this for one that was originally an acid, like if you had acetic acid acetate. You're not going to be able to find in textbooks the Kb for something like acetate, for the negative ions. What you will find is the Ka for their conjugate. Okay, so that one, if you had acetic acid acetate, you're going to set it up from the acetic acid point of view, where acetic acid goes to the right. For something like ammonia and ammonium, you're not going to find the Ka for ammonium in a textbook. They're going to expect you to be able to calculate it from the Kb of its conjugate ammonia. So this one, the second example, the one we just did right here, I could have equally done it using this cool little equation, right? And I would get the POH is equal to the PKB plus the log of the original concentration of HB plus over B0. Okay, so I'm gonna, pretty easy, so I'll go ahead and do that. Let me move this up. So go back to our page before, and we had our original two concentrations here of the ammonia and the ammonium. So I'm gonna write those over here, and we said that at equilibrium, the original concentrations, the initial concentrations, that's when you put the little 0, is very close to equilibrium because we're dropping the x. Okay, so this guy was 0.06, and this guy, his conjugate, ammonium, was 0.04. Okay, I'm going to put the m here for molarity, but I don't have to because you know whenever I put brackets or I do something like this, we're always talking about concentration. Okay? All right, so let's try it the Henderson-Hasselbalch way. So the Henderson-Hasselbalch way says the POH is equal to, POH is equal to the PKB, which I'm going to get in a second, plus the log of the conjugate acid on the top. Which is the conjugate acid here? This one, right? This guy has an ability to donate a proton. 0.04 divided by 0.06. And that's it. That's just that small ratio. Okay, so I just get 4/6, right? Okay, so first thing, I got to get PKB. So I'll do that over here. PKB is equal to minus the log of KB. KB is given to you. So PKB is going to be minus the log of 1.8 times 10 to the minus 5. So it's going to be like 6. Okay, we'll see in a minute. Okay, so what do? I take the LOG, open the parentheses, 1.8 E minus 5, close the parentheses. My LOG is just to the left over here, okay? Equals 4.74. So the PKB of ammonia is 4.744, so I'll leave it at 4. Okay, now here's something cool. This 5, guys, is reflected in the mantissa. So if you have 2 decimal places here, right, 2 significant digits, you get to keep 2 significant digits here. This number out in front of a log number reflects the, sorry, I'm spacing it, the exponent, okay? So you can have, keep 2 significant digits here, these 2, okay? So this is correct, right? Don't round it to just 4.7. All right, so coming back over here, what do I get? I get my POH is equal to 4.74 plus the log of 6/4, right? 4/6. So I'll take my LOG, do it all in one step, divided by 4 divided by 6, right, which is 2/3. I just left out all the zeros because they both have the same zeros in the front, equals. Okay, so this gives me negative 0.1 8. Okay, so I have to subtract 0.18 from here. So POH is equal to 4.74 minus 0.18. I get POH is equal to 4.56. pH is equal to 14 minus this, of 14 minus 4.56 equals 9.44. Not bad. Back on page 3 of the notes. Pretty good, right? Definitely good enough for us. Okay, so your choice. Don't have to remember the Henderson-Hasselbalch equation. You can do all of these just with a ice table, and the ice table is going to simplify immediately. You're going to be dropping x's all over the place with buffers. Good. Okay, so next page, this is called the general form of the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of the base over the log of the acid. You know this, right? Ka times Kb is always equal 10 to the minus, this is minus 14th. Okay, a little hard to see. Okay, let me sharpen up. And then that, the log version of that is pKa plus pKb is always equal to 14. Okay, here's another example. Take a look at it super quickly. What is the pH of a solution that is 0.2 molar in acetic acid and 0.2 molar in sodium acetate? So this solution is already made up, so there's no mixing. Nobody told you, they didn't tell you you have a certain amount of this and you have to mix it with that. So you don't have to do any dilution. They're already in there in those concentrations. Well, here's HAC, 0.2. Here's AC minus, right? So if you do it the old-fashioned way, you're going to get Ka is equal to this times this divided by this, right? We leave water out. We know that if I made an ice table, my x would be small, so I'd be subtracting x from 0.2, so that's going to be the same as 0.2. I'd be subtracting x from this 0.2. This is the one from here. This guy started out as 0.2. This 0.2 starts out over here, and this is the other x, right? So you're basically doing it really quickly. Well, look what happened. This divided by this canceled out. This is the concentration of the A minus, the conjugate base, right, over the original amount of the acid, right? So it's the base over the acid when you have an ordinary Henderson-Hasselbalch equation, right? When you're looking at it from the point of view of the acid. Okay, if those two things cancel out, then the hydronium ion concentration is just equal to the Ka. Look at that. There's the Ka, there's the pKa. If the hydronium ion concentration is 1.7 times 10 to the minus 5, what's the pH? Just take the log of that number, throw away the negative sign. You're going to get 4.77. Let's do it quickly the Henderson-Hasselbalch way. Henderson-Hasselbalch says pH is equal to pKa. Well, they gave you that. Right, so instead of using this one, like you did in the regular way, in Henderson-Hasselbalch you use everything is already, the logs are all taken already, right? Plus the log of the concentration of the conjugate base over the acid. That's this guy over that guy. Okay, well again, they're both equal molar, right? They're both 0.2. So 0.2 over 0.2 equals 1. The log of 1 is 0. So this whole thing goes away and pH is equal to pKa. There it is. So in a buffer solution where there are equal molar amounts of the acid and its conjugate base, pH is just the pKa. You didn't have to do any math. As soon as you saw that those were equal molar amounts, equal moles per liter, bam, that's the pH. Okay, so those are typically the way we make up our buffers is equal molar amounts so that they're just as good at buffering. They have a buffering capacity that's just as strong for the acid to soak up the strong base or for the conjugate base to soak up the strong acid, right? Why would we put them with one more than the other, right? Okay, next page is the derivation of the Henderson-Hasselbalch equation. Going to skip that. You can do that on your own. This is in your notes, page 6. Okay, that leaves me with talking about acid-base titrations, which we'll do for the second section. So that's what we're going to start, part 2. So this is a perfect video. It came out to 45 minutes, which is just about as much time as anybody can concentrate. Okay? All right. Thanks. We'll see you on the next video.